Please welcome all Juliette Leroux.
Yeah, so today I will try to show you that we can use one technology and study natural science from biomolecule to even building a quantum computer. And first, I wanted to start. Would it start? By showing a YouTube video of like small molecule, like small particles that are basically flying. So it's not in vacuum, so it's basically in a room, and you can see some small particles that are flying. In here, then we call like trapping. So we keep them in a space and we can move them around and observe. And what I will try to show you is how do we do this. So before, who am I first? I'm Juliette from France. So I grew up in Normandy here in a city called Chto. So you can see the town hall and the beach. Don't believe the image, Normandy rains. But I studied here until the end of the bachelor, and then I moved to Paris for end of bachelor and master before moving to Germany for my PhD, and now I'm staying in Hamburg for postdoc. What do I do for a living? I play with ion traps, and here you can see me basically working in different facilities, building those ion traps for experiments. So I work with photon coming from X-ray, so they come from large-scale facilities, and we work on basically 24/7 for a week or two, and then we bring outside of the way. And so this is what you can see is like setting the machine for running for 2 weeks, and then hopefully we record some nice data. And when we are recording data and everything works, we do a lot of team building, which is playing a lot of Mario Kart in the control room. So you can see a very important event of B time, which is Mario Kart race. So no one thinks about it, but usually a lot of scientists, they are not always serious. We love to also gather together and play. And when we don't do this, I want to show you that basically we can use one tool and do a lot of different science. So from studying very complex proteins to also see single atoms in a trap, or do some physical chemistry as studying this beautiful molecule that keeps me busy since like 4 years, or even build like a very tiny microchip ion trap and do some quantum computing. So you told me that a few of you don't know exactly what's a molecule, so let's go back to what I call the Lego blocks of matter. If, for example, you take a glass of water, then it's made of multiple small water molecules that we can call the building blocks. And as an analogy in here, you have more water molecule that you would have a grain of sand around all the beaches of the world. So in order to not look at it like as a macroscopic observable and see it, then we need some tools. And then water molecules, we can just break it even further into small atoms, like hydrogen, oxygen. And all of those atoms, we can even build them further apart and see this as a nuclei. So it's made of positively charged, and then we have the counter negatively charged, so the electrons that keep everything together. And basically we don't really need to know all of this, but charge will be an important role. So now it's neutral, and we can also go from a neutral molecule, kick out one of those electrons, and then have a positive charge. Because we remove one minus, then we end up with something positive. Or if we would add one more electron, then we would have something negative, and then the charge we can start playing with it. Because why does it matter for us? Like when we want to trap molecules, is the principle of two positively charged will repel each other, where two oppositely charged will attract themselves. And this is basically what is the building block of how do we trap a small molecule without touching it. We first give it a charge and we use electric fields. So we put a voltage onto, for example, 2 plates. One will be minus and one will be plus. And then we can use this properties of the charge, and then, for example, now we put our small positively charged molecule into our field, and you can see that now two positively charged will repel each other, and so the molecule will be attracted by the negative charge, and this we can do, and then flip the charges again of the voltage, and then do it again. This is basically going to, now we trapped it in 2D, so if we flip it fast enough, then the molecule will travel in this direction and we can keep it, but there is nothing to hold it to go out on the top or on the bottom. So now we don't need to do it in 1D, but in 2D. We do this by also implementing another two plates, and then we arrive in a configuration that are small charged particles and then trap in this 2-dimension. And if we then keep doing this by oscillating our two plates, plus and minus, then our molecule will be attracted by the minus, repelled by the plus. By swapping it, then we can keep doing this. So now you can see that our ions now have a motion that it will try to be attracted and do like a small circle around. And a good analogy for this is this small mechanical trap. So here you can see that if I'm not turning in the plus and the minus, then my molecule will try to go out. And if I find the right frequency, so how fast I switch my plate, then my ball will try to stay in the middle for a certain amount of time. So this is how we trap an ion, if I manage. And this allows us to keep it for some times and then start to play with it, making it, break it, studying it, identifying it. And you can even see that if I find another ball, some of them will be more stable, some of them will be less stable, and this allows us to also choose the one we want to study. By tuning the frequency, so how fast those plates move, then we can basically play with them and start choosing which one we want to keep, how long do we want to keep it, and if there are some more fragment process, or if they are bigger, they become bigger or smaller, then they will disappear because only one can stay in my trap. So basically this is the analogy. I can still move. And this comes from the YouTube video we saw. So this is the thing where we could trap some dust particle because they are statically charged as like statics that we can do between two persons. So we can just play with those two electrons and the ring, and this would allow us to trap charges, that big dust particle. But as I just said, we want to trap something we can't see. So we need to also do mechanically a bit of a better design. And for example, this is the 3D design of the one I used for my PhD. So you have like these two plates, as we saw, and instead of having 4 plates, this is the ring, and this one will be moving all the time and keeping our ions in the middle. So yeah, I 3D printed one. So this is basically 20 times the one I would work with. So you have the 2 plates and the small ion in the middle, and by always applying voltage, then the ion will stay in the middle of it, and the 2 small balls you can see is basically to bring them in the first place. We keep them for some time, and then we can kick them out and also detect. You can always interrupt me, by the way, and then detect the product of our interaction. So this one is in plastic, and we would just do it with stainless steel, so we can also apply some voltage on it. But else it's exactly the one that we would use for doing some spectroscopy on biomolecules.
But the angle of this lenses doesn't matter.
Yeah, it exactly matters. So to try to avoid that the molecules, so here the ball would try to leak out, because they always want to leave. So we try to have like electrodes that is a bit like this to have
and
them
the
less.
distance in between 2 lenses are always secure.
Yes, we also put them in a way that we have like the least amount of space where the ions can go out. So exactly. And we also want to play in vacuum, so it's not in interaction with any other molecules. So you need some kind of spaces, so we can use some big pumps.
So it's a neutral kind of space.
Exactly. So we need to trap them. We have them in vacuum in environment, so we have only all of them. Now that we code our ions, so what do we do in science with them? Because it's kind of cool, but else it's a bit useless if I tell you which is.
This is exactly the question I had in my head. Now what?
Now what? We have it. It's, as physicists, I find it already super cool, but else it's a bit
exciting.
What we can do, we can start to use it to identify some samples. So we have some molecule in there, but sometimes we also don't know. So it can also be used as something to identify, make a fingerprint of like the sample we used. For me, physical chemist, so I like to know how biomolecules are built, like what is the interaction with the water molecule and how does it influence the structure and processes in a more complex way. Or like quantum physicists likes to use it to build a quantum computer and try to understand and control and manipulate those atoms to start doing some simulation and go from a normal computer to a quantum computer. So identify, how do we do this? Imagine you take like a blood sample somewhere and you want to know what kind of molecules in there. So you place your unknown sample into a small container, mix it with water and some solvent just to be able to have it as one liquid. You use some technique to be able to bring them into your trap. So a technique that biologists like to use is called electrospray ionization, so we just put a lot of current on it and create some small ions out of it, exactly the way. So we remove one electron, they become charged, and then you can trap it in our ion trap. Then, as I said, it depends, like how you trap it allows us to measure its mass, because as big it is, we have to change the different voltage, how fast those electrodes are spinning, and it allows us to read what is the mass of the sample. Sometimes from the mass itself, we already know the compound, but if it's a very complex molecule, like a big virus DNA, then it's too big. The mass could be 12,000, and then we need to guess. So 12,000 could be a lot of things. So we can basically shake the molecule by introducing some gas or some proper vibration. Then the molecule will have some energy, and we can break it apart. And from how it breaks, it will give us not only one peak for the one mass of the full system, but multiple peaks. So a peak for this one, peak for this one. And by our big database, basically, then we can reconstruct, so we can take the puzzle all back together and know what kind of biomolecule it was. So here, for example, I choose coffee. So coffee is always important. We all say that scientists basically runs on coffee, so I thought it's a good example. So you have the full molecule, you break it into pieces, then I will know this one is one peak, the other one is the other peak. If I sum them all, I go back to the official mass, like of this one biomolecule, and I know it was coffee. And this works exactly the same for big viruses, for big proteins, DNA, and every compound you can find, we can always identify them like this. So this is a lot of what the biologists are doing when they create new proteins or want to see something happening to their very big viruses they were creating for the last few months. They usually first do such kind of experiments where they start understanding if what like they wanted to build is actually what they built. Before they do even more 3D imaging of their biomolecule, usually they already want to know what happens and what it. So this is the identifying, like lots of police and stuff they like to use, biologists, pharmacists, and what we can also do is not vibrate them to break, but we can also use light to allow us to look at other processes. So for example, you might have seen it somewhere that light is basically a frequency. So you have radio, microwave to warm up your food, or X-rays, and we can basically use all of this to control and to also look at different small processes happening into the molecule. For example, what I've been doing over the last few years is trap this one molecule called phosphotyrosine, which is one amino acid present in proteins, and so in your body that likes to control the way the protein will fold, because they are not always linear, but they can have different conformation. And I usually add one water molecule to see how water will influence how it looks. So you can see here the picture of the ion trap that is moving around. And then introducing phosphotyrosine with one water, and we never introduce the same one, they always move around. So we introduce a bunch of them that have different three-dimensional structure that we call conformers. And then they move around, and we use light coming from one of these big facilities, X-ray, to try to understand what is the difference. If I put one water molecule, if I remove it, maybe there is multiple ones that exist at the same time, and I can also break it to know how it breaks. So this is like proper data where this is phosphotyrosine again, so yeah, almost look like this. And because we know the mass, phosphotyrosine has one mass, this is this one peak, and if I have one water molecule, it's heavier, so you have a peak at mass 18. Yes?
Actually, I think with this part, how do you add like one water molecule?
How?
Yeah, like.
So you have all of them in my small sample, right? And before I put them in the gas phase, where like the trap is and where you have the water molecule, you have some ways to basically do it very gently. So you keep it with you, because as the molecule was already in water before, you have a way that if they're very stable and you're very gentle while bringing them into your trap, you keep it with you. So this is the easiest way. Or you can keep it in the trap, so you already have your phosphotyrosine moving around, and then I can put some water on top of it in the trap, and they will die.
Okay, so like this one molecule, it can interact with it or something. I didn't get it. Like,
It
it's
can.
like you're sure like it's only one water molecule.
It's only one, basically.
Okay.
And it can also, the water can also live around and not interact with my phosphotyrosine indeed. This is why we have the mass. If I see a peak with like the mass of phosphotyrosine and water, I know they are one compound. If I see it without, then it's phosphotyrosine alone, and there might be also some water around. But as my ion trap, I can basically select what I want by moving the radio frequency around. Then I can also kick out what I don't want to see. Right? So now I only wanted to have phosphotyrosine and phosphotyrosine with water. So everything that was produced, I didn't want to see it. I kicked it out by changing the voltage on my two electrodes. And then I introduced some more energy to my small system, so I can break it the way as we did it for identifying, and then try to play what are all those peaks. And we saw that we have this part of the molecule with water, some other parts, and basically this also tells me that depending on what kind of external field I bring, the molecule will break differently. So depending on if it has water or not, if it's like such conformation or not, this will give me a different pattern of these small masses. So how it fragments is also a fingerprint of how it was at the beginning. Now we can shoot with X-ray light, and X-ray light compared to the normal light coming from the sun allows us to also decide where on the molecule I will shoot with the light. So if I do it on all the black ones, basically I will get such a spectrum, and this tells me how did it break, what kind of structure it has, and if I compare with some simulation that the theory people here likes to do, or I also do like to do, then I can also say that my calculation coming from theory really match also what I see experimentally. And this theory spectrum tells me how the structure was. So I compute a structure, it gives me a spectrum that I can compare with experiments, and this tells me if such a conformer or such a three-dimensional structure exists or not. So here, for example, you have like the phosphotyrosine, like this, and then depending on if the water is on this side, or making such a bridge and leaving basically in the middle, if it changes something and if it exists. And so here we just concluded that the water usually likes to stick in the middle. And this is already something that is interesting because for biomolecules, they usually lives in water. So if you tell me that you study phosphotyrosine without the water, it might have some structure. It doesn't exist when it's like bind to another molecule or in our body in water. And once you have this three-dimensional structure, then you can also start to do some more complex experiments and understanding how fast this water is moving in between, how many water do you need for the structure to be completely fixed. And this is usually what I do with Nicola here. So this is like some kind of thing we can do is like you imagine now we did it with 0 and 1 water, and we can keep adding them one by one and see if it would change something. And this is usually the foundation to do some more complex, study some more complex molecule that will have tens of those, or have even more water molecule around, and see how such a small biomolecule evolve in water.
How old is this technology? How old is this technology? How long have people been doing this?
Ion trap was developed 120 years ago.
120 years ago.
Yes, 1905 by the person who gave the name to this trap is actually called a coal trap from Wolfgang Paul, who designed the first one, and he even got a Nobel Prize for it because it's really nice and it can help from identifying to what I like to do, which is physical chemistry, or even, I think I was faster than I wanted, even build a quantum computer. So you have multiple type of quantum computer. I don't know, but one I can relate to is the trapped ion quantum computer. And this exactly works the same way as what we've been doing, but instead of like trapping such a big thing, we will trap basically one atom, one single atom, and trap many of them. And here you would have your ion trap, and in every trap you will have one atom. One laser will come and basically build a 0 as the classical bit of a computer that is a 0 or 1. We can do the same thing with atoms. Use a laser to bring them to a 0 position as they still move a bit. This basically prepares our atom to be a 0, and then we let them evolve, and that will be basically 0 or 1 or both of them at the same time. This allow quantum chemistry, and then we will use another laser to read if the atom is a 1 or a 0. So basically this is how it works, and then they can make multiple of those quantum bits interact with one another, and this is how they build those quantum computers. This exists in real life, so you have two commercial things available already from two companies where they managed to put 50 different traps together in a small in a small chip. So this would be probably that big because they managed to 3D print very, very thin ion trap, not as big as this one or the one I used that are vortex, but they managed to put hundreds of them in probably 10 centimeters and control and read. And I've learned a few weeks ago that you had two that are commercially available that if you find a few million €, I guess you can even buy. and I don't know much more about quantum computer, but it's using the same techniques, and we get from identifying atoms and molecules. And basically, we can go from having one atom that misses an electron and do many different kind of science. So from identification of small unknown sample to some physical chemistry to even do control and build a quantum computer. So it's one technology that you can use for multiple research topics. And this was it for me. The others are more complex.
But one step back, how you capture the ion, how you localize it, and how you make it work alone out of the complexity of the connections with other.
What do you mean by how do I make the?
What is the, like, how do you trap the ion? Like, what is the technique to trap the ion? The single one.
The single technique to trap the ions.
I think the question is similar to what you asked. It's like how you make sure that it's only one, or how you make just one.
One type of. So in the trap itself, so here in my analogy, I can only trap one.
Yeah, I mean,
right?
it's big, it's physical. It's physical. For me, it's easy to understand.
On another one, if you don't count quantum computing, in such a one, we will trap 10,000 of them.
Yeah.
But because they are all charged, they will repel against each other. So they all live on their own inside the trap, but we still have 10,000 of them. But we make sure we have 10,000 times the same one. So we can assume that it's the same one all the time.
It's still the assumption, though.
Exactly.
It's like in art. It's like an art.
Yes.
It's still the assumption.
And this is why I was saying that the same, because I trap one mass. I know that I trap one mass because this is given by the frequency. But I never know if I trap this one, this one, this one.
Yeah, whatever
this
combination is.
Exactly. So usually we have a ton of them. So for small molecule you have less because they are less flexible, and the bigger your molecule will be, the more flexible it will be, the more we have. So either we design, once we design our experiment, something that won't move, or we live with the fact that there is a lot of them and we have to guess. This is where we also combine with simulation to know which one are the most probable. And with our different kind of light, if I shoot at my carbon or with oxygen, I can try to make the puzzle back and see how many of them are very different. But all the very tiny thing, if this move like from this to this, I don't know. I live with.
If I understood this correctly, what you're doing is you're trapping the ions, and then you're performing some kind of action on them and taking the data, and then seeing if the data matches like what you predicted would be there, or different things. And then you had that graph that showed you the distribution where if there was this one spike, well, there was this thing, and there's also when there's the big spike, you know, you've got the whole thing. When there's the big spike, or the next even bigger spike, and you've got the whole thing in water.
Yes.
And then the fragments that showed you. So it's about like taking measurements or performing actions, taking measurements, and then seeing what kind of data you get out.
Exactly, and the technique is actually called action spectroscopy. Because we record the action of something on the molecule.
And you're shooting light at it, or you're throwing water at it, and then see what it does.
Exactly. That's the official name, action spectroscopy.
Fascinating.
If I understood this correctly, I mean, an ion is basically a positively charged molecule.
Yes. I mean, they are negatively charged, but I love positive.
I mean, at the very beginning, you laid that out, but at the end, I'm like, did I understand what an ion is correctly?
Yes, exactly. No, this is exactly this.
Yeah. Okay.
I have a question. Is it a different technique from mass spectroscopy?
No, this is called mass spectroscopy.
So it's I never knew that you needed the iron trap for mass spectroscopy. I thought it was like all in the flow you that you shoot some ionization.
So we would love to do this because this would also allow us to directly map how they look.
Yeah.
But the problem is that we don't have, if you would just look at them on the fly as you suggested, then there are not enough of them that we can measure compared to the rest of the things that are in vacuum, because we never have perfect vacuum with only this one molecule, but there will be also some what we call a residual background. And if we do it on the fly, then we don't see. So the technique is we trap a lot of them, assume they are at least all the same mass and roughly the same kind of way to fragment.
It's just very interesting because like in student books we always explain mass spectrometry like it's something on fly, right?
The people that this is one of the flavors.
I mean, you can also do what we call a mass spectrum of a molecule that would be neutral, so you don't trap it, because if there is no charge, all my technology is not working. This you can do, but you can't do it on very big molecule, because the problem is you can't put them into the interaction where the interaction takes place in the first place. So mass spectroscopy was developed to really, and this ion trapping, at least for biomolecule or biomolecular reason, we had to develop the trap so we can actually put them in the vacuum in a sufficient number that we can get something.
How do you actually measure like you shoot up the molecule it falls apart, like what you couple this because like you can lose stuff from the ion trap.
So this is why we love using what we call the pole trap as the very first one that was developed, and not a linear one, but one that is really this ring, because we can select first the first molecule, then it will fragments because we shoot with lights, but this one has the particularity that we can keep everything that is smaller also in the same trap. So we keep them, and then we kick everything out, and not only our molecule, but molecule plus fragment into this time of flight mass spectrum.
So you coupled it to the time of flight.
Yes, but you don't have to, because you can also use the better one, the one I use for my PhD, for example, that can do everything, which is by moving a bit the radio frequency field, so how fast you move these electrodes, then you will kick them out one by one and read the mass. So you can kick out every masses of your spectrum. So if we go back to here, let's assume this is all the molecules I have trapped into my trap because of the light, and then I will first kick out 40, 41, 42, and read how many of the 42 I have. And this will give me like something that you have 0, I kick out 42, I have some points, then after 42 goes back to 0, 43 I have nothing, and then I can also build it without the classic time of flight spectrometry. You can also just do it by tuning those 4 electrodes. This is what the biology people are doing. So they don't have time of flight, they just have a mass spectrometer with another set of, instead of having these what we call extraction, so those 2 ones, you will have a double pair, and the other one will do what we call a resonant extraction. Keep them out basically just one by one, by tuning just a bit the different voltage between these double 2 plates. And this is like what all the biologists like to do, because it's even more accurate than kicking them all out and read the time they take to fly to the detector.
Fascinating, enigmatic.
I lost this.
But I mean, what is the difference with the multiple pole traps that this one is?
Basically, not normally you would keep them all fixed, so plus 500 volts, and this one is the only one that will flip this sign with like the radio frequency, and if you have two double plates, then both of them are coupled to radio frequency as well. And then we can go back to my first example with my 4. And basically we will go exactly into this regime that they will all move around. Where normally if with this one, those two will say plus, and this one will be the one with the transitive count. And if you have double plates, then we do exactly this by flipping both sides.
So, like, on the central ball, you essentially have, like, somehow space around, like, the different charges.
Yeah. I mean, basically it rotates. I don't know. Robert usually explain it much better than me. But the central ring is the one with the radio frequency.
So like, essentially, you kind of have here, like, glasses, or how happens? I mean, like, you don't have, like, have a physical different...
No, you just alternate fast enough that they all see a plus and minus at the same time, and then the molecule will do a kind of a neat shape.
I have a question about I guess the frequency would depend on the size of your ion, right?
Yes.
And how do you choose the frequency? Do you make it experimentally? And is there any computational prediction on
Yes.
what frequency you need to put in your experiment?
So there is always, as you know, the difference between theory and experiments.
Yeah.
It's derived from equation. They are called. I didn't write them down, but it's called the Mathieu equation. And so you have it defines basically the motion of your particle, your charged particle into such a quadrupole. And we have a diagram called stability diagram that tells us exactly where we expect the ions to be stable. And so then it will give us like the set of parameters we need for those two caps and for the radio frequency. And basically we get this from theory. And it depends a bit on the shape, but this stability diagram we always use at the beginning to not be completely blind. And then we test it and we adapt it to the theoretical value. But at the beginning, we have the equation for this.
Is it like you need to be faster for small ions and slower for big ions, or it's not working this way?
Good question. I don't remember.
I mean, you can check with the mechanical analyzer, right?
Yes.
So you don't have an analytical solution to the Mathieu equation?
Huh?
If it is a Mathieu equation, so you don't have an analytical solution, so you have, like, numerical estimates.
Yeah, we have estimates and then you guess. But I think yes, you need slower frequency for bigger one, faster. Did I say something stupid or not?
No,
I think this is this. Yeah, you need faster rotations with faster radio frequency for smaller one and slower for big ones.
It's like smaller molecules will move much faster.
Yeah.
So you have to switch, like, basically the rolling uphill much quicker.
Mhm.
They roll uphill over time. And then for bigger ones, you have to go down as they keep
And then depending on the geometry, then we can trap some of them at the same time, but they need to have like relative mass. So we can't trap something that is 12,000 and something that is 20 at the same time. This is too far away from one another.
We will lose something.
We have to choose what we lose, yes.
Since we're talking about ion traps, what is a beta?
Penny traps?
Yeah.
So
Is it also similar to that?
it is similar, but you won't only use electric field, but you will also use magnetic field. So this is basically the difference. Is here we only use voltage and electric field radio frequency, and pinning also use magnetic field as well.
So less pleasant to work with. Less pleasant to work with.
I've never worked with a pinning trap. But I think everybody prefers only to have to deal with one problem and not two.
How is it different from coating?
From cold trims,
Because you need
cold trims means reaction microscope. So you have like your molecule flying, then you interact with some lights, and then you will record the ions on one side and the electrons on the other side, right?
We use both
You,
electric and magnetic field.
yes, you'll use them electric field and magnetic field depending on how you push them, and then we don't have nitro. Because this is the main problem. As soon as they are here, if some electrons flies off, they will bump into these electrodes and I will never see them. The only thing I see is the results of the light on the molecule at longer time, so only fragmentation.
So you told that you investigated this molecule at your PhD research and you apparently spent a lot of time, but what did you find? What was the main like outcome of this? So you told that it goes as a reach.
Exactly.
But what, like, do you know what does it mean for biologists or for?
So during my PhD, I didn't know. The idea of my PhD was actually to try to build a setup or build a source and a way to do it to actually get this water molecule, because the technique was to put like molecule in the gas phase without their water. This is the mass spectrometry works that you don't want the water around. And then my PhD was trying to do the opposite, try to put water back. And so this is already quite hard, and so for my PhD I proved that you can do this and you can probe the results with X-ray, and that this water, this is what I now do with Nicola, which is trying to understand what is this bridge structure giving to some more fundamental processes, which is like some charge transfer, some proton transfer, or this water, now that it's linked to the phosphate, what does it do actually to the molecule more than it's placed here? So we learn that the electrons that are sitting around here, they can delocalize to the other side, or if we put some more water molecule around, then the electron will leave and create some ultra-fast processes into the molecule. But from just mass spectroscopy, you don't learn much about this. We mostly learn how to put them in the gas phase and what is the three-dimensional structure.
You think you never find a molecule that you love as much?
At some point, I will have studied everything that you need to know on phosphotarism, and I think we start to run out of ideas. I think we spend enough nights measuring this. So probably I should find something more interesting at some point. But I like that it has everything, so it's a small biomolecule, one of the building blocks of big proteins, and it's small enough that we can still perform some calculation and that we can still understand the spectrum that we record. And if we go to a very big proteins, then at some point everything is onto one another and we don't know anymore.
What is molecule on the hat?
No. Water molecule were on my PhD hat, but not phosphotarism.
You didn't have enough building blocks?
I had a few water molecules, but I didn't have because it was just the end of my PhD where I started. Before, the idea was just to do nanosolvation, so I did other kind of project that I did on a PhD thesis. But I spent more time with this, but didn't show the most results that I had to put in the PhD thesis. And now I should, if I would do another one.
Makes sense. More questions?
Who wants to play?
So, I guess we'll talk no more.
No.
Okay. So then, thank you.